And Shahind all, my name is Arun Kumar Maurya, Assistant Professor in the Department of Electrical and Electronics Engineering at EKGC, Ghaziabad. In the continuation of the lecture series of Power System 1, which is focused on the interview type questions and which will helpful for uh, placement drives and as well as in the competitive examinations. So the topic is insulated cables. So this is very important for electrical and electronic engineers graduates and also helpful for the power system protection students and may helpful for MTech graduates also. So in this case, we will discuss the insulation resistance of a cable, what is the capacitance of a single core cable, capacitance of three core cable, and effect of capacitance in underground cable, and the dielectric loss in a cables. So these are the contents. So if we talk about the insulation resistance of a cable, so the resistance offered by a cable to the path of the leakage current is called an insulation resistance, and this figure shows the section of a single core cable which insulated with the help of a layer of an insulated material. So we will see that this is the core side, and this is the dielectric leakage current, that is I dielectric of leakage current, and this length, this is the circular part, and this length is radius r, and the total length is, which is the vertical line, and it is the r, capital R, and this is the layer of distribution. So in this insulation resistance of a cable, we will see to calculate the insulation resistance. Let us consider an element section of a cylindrical cable of a radius x and the thickness is dx as shown in the figure. So in this case, this is taken to be as small x, and the derivative part of this one, and this is to be taken as dx. Let d equal to diameter of a conductor or core. So this is the core side, this is to be as d, this is the diameter, and r equal to d by 2, and capital D equal to diameter of with sheet, and which is capital R equal to d by 2. So in the other cases, as the leakage current flows radially outwards, the length along which the current flows in elementary ring is dx. So this is the elementary one, this is the dx, and this part is x. This is the elementary ring. While the cross-sectional area perpendicular to the flow of current depends upon the length one of the cable. So the cross-sectional area equal to surface area for the length L of the cable, that is 2 pi x, basically 2 pi RL, but in this case 2 pi x into L. So 2 pi x L. Hence the resistance of the elementary cylindrical cell is dRi, derivative of R, rho dx divided by 2 pi xl. So where rho is the resistivity of the insulating material. So this is important formula while we use the insulation resistance of a cable. And if we see the derivation part of it, so Ri equal to integration from small r to capital R, which we have shown in this figure. This is small r and this is capital R. So Ri insulation resistance is taken as dRi, which is derivative from R to R. So Ri equal to R to R, and what is dRi, which we have seen the rho dx 2 pi xl. So rho is constant, so rho is taken to be outside dx by 2 pi xl. So Ri equal to rho by 2 pi L, integration of from R to R dx by x. So Ri equal to rho by 2 pi L ln x, and which ranges from R to R. So Ri equal to rho by 2 pi L ln R minus ln R. So that is Ri equal to rho by 2 pi L ln capital R by R. So Ri equal to rho by 2 pi L ln, this is the property of logarithm, ln n minus n equal to log ln m by n. This is the property. Ln capital R by R. This is the formula. So the insulation resistance is rho by 2 pi L ln capital R by small r. So if we see the capacitance of a single core cable, so let small r equal to radius of the inner conductor, and this is d equal to 2r, d equal to 2r. This is the radius, and if we see the r plus r, which is d, so the d equal to 2r and r equal to d by 2, and capital R equal to radius of the sheet, and which is d equal to 2r. So this is the capital R, so which is equal to d by 2. So d equal to 2r, which is the dia. So if we see the dia r, so 2r equal to d. So this is the capacitance of a single core cable, and if we see that derivation part of it, to Ex equal to Q by 2 pi epsilon naught epsilon r into x volt per meter, and the V is which is the potential difference, such as the voltage. So Ex into dx, which is to be taken as dx, and which is from r to r, and Q divided by 2 pi epsilon naught into epsilon r taken to be outside into dx. So Q upon 2 pi epsilon naught epsilon r ln r by r. And what is C? C equal to Q by V, charge by voltage. So C equal to Q by V equal to Q divided by Q, and Q upon 2 pi epsilon naught into R into ln r by r. So C, capacitance equal to 2 pi epsilon naught into epsilon r divided by ln capital R by R. So and the unit is farad per meter. So C equal to 2 pi epsilon naught epsilon r divided by ln R by R. And xc equal to 1 upon omega c and omega equal to 2 pi m. And this is a capacitance of a 3-core cable. So in this case there are 3 conductors A, B and C, and this is to be CS, and the neutral is CC. So this is the sheet and there are the conductors and this is the equivalent of it. Consider a 3-core symmetric underground cable as shown in the following figure 1. The first one is, let us see is the capacitance between any core and the sheet, and CC is to the core capacitance, that is capacitance between any 2 conductors. In the above figure, second figure, the 3 CC is core to core capacitance and delta connected, and the core sheet capacitance CC are star connected to the sheet, forming a single point which is neutral in, and this is neutral point. And which is point is in the figures second and third. And this is other side. Outer points A, B and C represent cable cores and the point N represent the sheet shown at the middle for simplification of the circuit. Therefore, the whole 3-core cable is a equivalent 3 star connected capacitors, each of capacitance CS plus 3 CS as shown in the figure third. We can see this is neutral point, that is A, B and C. The charging current can be given as IC equal to 2 pi F CS plus 3 CC into V phase ampere. What is I? I equal to V by Z, pi V. What is Z? Z XC. What is XC? 1 upon omega C, and omega C actually the XC, the capacitor reactance should be taken as 3 CC plus CS, 3 CC plus CS. So IC equal to 2 pi F CS plus 3 CC into V phase amps. And it's the effects of capacitance in underground cable. Capacitance is inversely proportional to separation between the plates. If the separation between the plate is large, capacitance will be less. So the formula is CKA epsilon 0 by T. So in this case, if the separation between the plate is large, the capacitance will be less. So C is indirectly proportional to 1 upon D. Okay. In overhead lines where 2 conductors are separately via several meters, the converse of the course is also true. If the separation is small, the capacitance is more. In underground cables, obviously the separation is relatively smaller. Hence, capacitance of underground cable is much more than that of overhead lines. And other part is dielectric loss in cables. In that dielectric, for example, insulating materials, when subjected to a varying electric field, will have some energy loss. Obviously, it has a energy loss which is to be seen as a dielectric loss in a cables. The varying electric field causes a small rearrangement of weakly bonded molecules, which lead to the production of heat. So the loss occur, and which is to be seen as a electric loss in the cables. The amount of loss increases as the voltage level is increased. It is directly proportional. For the low voltage cables, the loss is usually insignificant and is generally ignored. For higher voltage cables, the loss and the heat generated can become important and needs to be taken into considerations. So the dielectric loss in a cable is measured using what is known as the loss tangent or tan delta. Tan delta is the tangent of the angle between the alternating field vector and the loss component of the material. So the higher value of a tan delta, the greater dielectric loss will be. So which is WD dielectric loss equal to omega C V naught square into tan delta. So the higher the value of tan delta, the greater the dielectric loss will be. It will increase. So V naught cable related voltage to the earth, that is to V naught B, and WD the dielectric loss per unit length, and tan delta loss factor for insulation, and epsilon insulating relative permittivity, and omega equal to angular frequency 2 pi f. So this is the dielectric loss. So in this lecture we have seen the insulating cables and insulating resistance formulation and the capacitance formulation, and we have seen that dielectric loss in the cables. These are the points. These are the typical formulas which are used for your interview preparations and the placement drives. So these are the small points, but make a large impact on your profile, which you have a strong interest and a strong and a sincere study on these topics. So these are the very important, I believe. Thank you.